really gonna sit down for a while, catch my. Get my.
Okay, any questions from last time? Oh, let me kind of play the math clip today. We got this homecoming business going on. Teacher Cook, who is a pretty new professor, I think this is her second year, is going to talk to us about how many of y'all, I'm kind of curious, how many of y'all have ever done a poster presentation at some point, right? Never done one? Yeah, so I think this is getting actually more common that people do this. And of course, you have to do this work too. What might be the most interest to some of you grad students is if you go into industry, you know, this is probably a good way to sort of sell your ideas. And number two, some of you might be mentoring people that have to do poster presentations. So anyway, so it's worth a look. So I encourage you all to be there. So the last time we talked about Krull dimension. If you have a chain, frequently increasing chain of prime ideals of this, we call this length n. And the Krull dimension of a ring is a supremum over all chains of primes with length n. So you take supremum over all such n's. Actually, so you can obviously you can generalize Krull domain, and you can talk about well, so example, I think of this. Well, let's just. How about the Krull dimension that? Well, certainly. Let's call this R. Is infinity. Because I can give you an infinite chain of prime ideals. Okay? So I've certainly got countable chain of prime ideals. But the Krull, so I give you this example to show that you can sort of generalize the notion of Krull domain in a very, or Krull dimension in a very natural sort of way to talk about how much higher you can make. There's a countable chain of primes. So the Krull dimension of this actually is uncountable. Does anybody see how to give an uncountable chain of primes?
Do the same thing with a rational.
That's right. So I don't see a way to do it with this index set, although you can. Right? But let me re-index this. This is enough to make blood boil, I think. So look at, well, we'll say R prime. So now what I'm gonna do is instead of indexing the variables 1, 2, 3 like that, I'm gonna index the variables with positive rational numbers, all right? Everybody okay with that? Notice that R prime and R are isomorphic, right? Because there is a one-to-one correspondence between the variables here and the variables here. So just set up a set theoretic map that maps the natural numbers into the positive rationals and use that to induce the isomorphism. Everybody okay with that? Now, let take any positive rational number, or I'm sorry, any positive real number, and let P sub gamma be the ideal generated by X of the alpha, such that alpha is less than gamma. Right. So for example, if gamma is, I don't know, the square root of 2, then you take, that should be X sub alpha, my bad. If gamma is the square root of 2, then you take every rational number less than the square root of 2 and use that to generate this. If gamma is 3/2, then every rational number less than 3/2. We can say less than or equal to, so it's not silly, right? But it doesn't matter. Notice that these are all prime. It's easy to see they're all prime, and if gamma 1 is less than gamma 2, then P gamma 1 contains P gamma 2. And basically, you can index this chain of primes by positive real numbers, right? Which is, I don't know about you, but I find it a little bit disturbing, right? But nonetheless, you can do it. This has got a very big Krull dimension. I can stack them uncountably high in this case. Okay, so that's kind of some interesting beginning stuff here. Proposition 4. 2. Let R be a domain with quotient field K and X an indeterminate. By the way, as I write these definitions and theorems down, what I'm doing is I'm going to give you really a fully groovy theorem about the Krull dimension of how a ring relates to its polynomial ring. I want you to be cognizant as you go on. Ask yourself at when I do this proofs and stuff, does this work for power series? Right, so see if you can fix the proof to make it work for power. So let R be a domain with quotient field K, X just some indeterminate, and there's a one-to-one correspondence between prime ideals of Rx of Rx that contract to 0. Contract to 0, that is to say, so these are just the prime ideals that contain only the zero constant term, and prime ideals of Kx. So, and this correspondence works this way. So let's prove this. Let's suppose suppose gamma is a prime contracting to 0. And it's a gamma intersect R at 0. And you can say domain here, didn't I? Yes. And S, so suppose that we have one of these ideals, gamma that contracts to 0. That just means that the only element of R that's in it is 0. Let's let S be the set R minus 0. Note first, R localized at S is equal to K, because now we're allowing every non-zero element to get a denominator. And notice that if S is a multiplicatively closed set of R, it's certainly a multiplicatively closed set of the polynomial ring. So what is this? This means polynomials over something in S, right? Polynomials over this constant. How can I rewrite this? Yeah, I hate these kind of questions. What am I thinking? How could I rewrite this? Right. By the way, the fact that this is contained in KX is pretty clear, because what an element here looks like is A0 plus A1X, AN over S. So you can write each of these fractions and say, hey, look, it's in KX. Do I agree with that? The interesting part is the other way. What's it?
I'm sorry. So I'm saying this is where we need polynomial. This is where this won't work for
Right. Right. This container will work with power series, but the other way is not going to. Like, if you have A0 over S0, A1 over S1X, AN over SNXN. Oh, it's a typical. Yes, you can put it over here by finding a common denominator for the S's, right? With power series, there's no real guarantee. In fact, to be able to do that in power series, it's a very, very strong condition on ring, right? It's almost never true. You can do it for fields, for example, and there are some other domains, but in general, for the integers, even something as nice as the integers is hopeless, right? So it's a good observation. This little step right here, power series is not going to work, or one doesn't expect it to work in general. Right. So let's get back to this. We want this one-to-one correspondence between primes of Rx that miss S and primes of R of KX. So now here's the way the correspondence works. Gamma gamma goes gamma localized S. This is the way that this correspondence works. So notice that gamma localized S is basically just a set of gamma X over S, where gamma X is the gamma and S is an S. Notice it's easy to show that this is an ideal. In fact, we've seen in general that phi is an ideal, but now localized S is an ideal, and is prime. So it's an ideal that means the exercise. The fact that it's prime is suppose. Let's say. K1 of X times K2 of X is in gamma S. Right? Then. Let's write this way. R1X over S1 times R2X over S2 equals Rx, well, we call it gamma X over S. Right? Again, I'm sort of taking advantage of this over here by saying, okay, any element of KX can be written as something, a polynomial over R over a single denominator. Right, so I've rewritten this, I collected the denominators like this, right? And what this gives me is S R1X R2X equals S1 S2 R of X, I'm sorry, gamma of X, which is in gamma. Because gamma is. Therefore, S R1X, R2X is in gamma, which is prime. And notice that S is not in gamma. And why is that? What's my assumption about gamma that lets this albatross fly? Well, S after all is a constant, right? And gamma doesn't contain any non-zero constants, right? So this is not in gamma because gamma contracts to zero. So S is not in gamma. Therefore, R1X, R2X is in gamma. So without loss of generality, R1X is in gamma. So K1X, which is R1X over S1, is in gamma F. And so gamma F is prime. And so every gamma corresponds to gamma S. Right? And how do we know, how does the correspondence work in the other direction? On the other hand, here, let's say A in KX is prime, then A intersect R must be zero. Somebody tell me why? That's right. Let's suppose just for giggles that A intersect R is not zero. So you've got some non-zero element in A, right? It's also in R. But as an element up in KX, it's a unit, which means that A would contain a unit and therefore can't be a proper prime ideal. And so the correspondence works this way. Gamma goes to gamma S, and gamma S goes to gamma S, intersect R X, which is gamma. And that's easy to check that when you intersect gamma S back down. So this is the one-to-one correspondence that we have craved. And notice, as Jared pointed out, this is a little bit iffy for power series, right? Because I did use some polynomial stuff that didn't seem like it's going to fly. Okay. Any questions on that? Here is a corollary to this, which is a really pretty little piece of work here. Corollary 443. R is community. One. Then there is no chain of three prime ideals. All lying over. Three prime, you know, R X. By the way, let me point out that it's fairly easy to give examples of chains of two primes that lie over the same ideal down below. Let me give you an example. Okay, so let me make a prime ideal. Everybody agree that the ideal generated by two is a prime ideal. Can anybody give me a chain of two prime ideals in ZX that both contract to this?
Ideal generated by two, and the ideal generated by two and X.
There you go. So the ideal generated by two, shall I display for dramatic purposes, and this is just all polynomials, all of whose coefficients are even, right? This is a prime ideal, strictly contained in the ideal generated by two and X. Notice this is strict because X is in here but not in here. Both of these intersect down to the ideal generated by two, right? So there's an easy way right there to see that, yes, I can get two different prime ideals, two comparable prime ideals that lie over the same prime ideal. And that was so easy, you could think that maybe I could build it bigger. But what the content of this corollary is, you can't do that. You can't have three distinct prime ideals that all contract. And this is going to be a very important step if you want to understand polynomial dimension. So this is a beautiful exercise in sort of reducing. And so I'm going to, you know, I've blotted out several problems, especially when we were working on Nostell and stuff. Let me go through this a little bit more carefully so you can see kind of the coolness of it. So suppose gamma 0, gamma 1, gamma 2 are prime ideals. All lying at 0, or all lying over 2. And of course, since they lie over P, that means that their intersection to P of course, since these are prime, that automatically means that P is prime. Okay. So here's a reduce problem. So this is, I've talked about how to do this before, and now I'm going to kind of carefully go through it a little bit and kind of explain what this is all about. So let's reduce this problem by passing R mod B. Right, because notice in our corollary here, we don't say anything about where he said it's communicable identity. It could be full of zero divisors or whatever else. And let me make this more precise. Notice that as P is contained in gamma I, right? Because each gamma I intersect down to R is P, so that means that P is contained in each gamma I, right? Then the ideal PX with prime and RX have RX mod PX is isomorphic to R mod PX, which is the domain everybody agree with that? So, PX is a prime. This is the analog of the example I did where I did the ideal generated by two. These are all polynomials. All of these coefficients are in D. So because here's what we've got. We've got PX is contained in gamma 0, contained in gamma 1, is contained in gamma 2, right? We've got that for sure. Everybody agree with that? And so I didn't say anything about 4 primes, I just said 3. So what I'm going to do is I'm just going to replace this. So there exists a chain of primes. So now I'm just going to replace the smallest one with PX. Right? Right, so I'll place the bottom of that. So now I've got another chain of primes, and I can get my hands on this last one. So note that R mod P is a domain because I'm modded out by a prime. So now I'm in a more comfortable area. And in R mod PX, in R mod PX, PX corresponds to the 0 ideal. Because this is the same thing as if I morph RX minus PX. And gamma 1, gamma 2 correspond to and gamma 2 Everybody okay with that? So now, Px corresponds to the 0 ideal, which is prime because R mod Px is a domain. And now I'll get these two non-zero primes, right? So let me kind of revamp the situation here. So we've reduced to, decide a chain this. We can find, and I'm going to use the notation here, a domain. That's the middle of this. Domain D. Such that there exists a chain of primes. Everybody okay with that? So now what I've done is I've modded out my P and I've reduced this down to the case where this is role R mod P. I've now got a domain. And I have a chain of primes starting with the P of X business, which is the 0 idea here inside Q1 inside Q2. So I've got. So now I've reduced this to if there exists a chain of 3 primes in the polynomial ring over any commutative ring with identity, I can get a chain of 3 primes in the polynomial ring over a domain. Anybody see a problem with that? So that's the important field. And let's refer back to the theorem that this is a correlator. All 3 of these primes now lie over 0 in D. Right? Because basically they correspond to the P and R mod P is the 0 ideal in D. So now what we have a chain of 3 prime ideals in DX now lie over D. By theorem, this corresponds to a chain of prime 0 in Q1 localized at S and Q2 localized at S in Fx. Right? Because remember that theorem says there's a 1-to-1 correspondence between primes of Rx that miss they contract to 0, which all 3 of these do, and prime ideals in Kx. So this gives a chain of 3 ideals in Fx. What's wrong with that? This is actually kind of a neat proof that the algebra, because we wiggle around and we've changed our scenario until finally we've got to a scenario where it's ridiculous. What's ridiculous? What's that? Yeah, that's exactly right. What do we know about Fx? It's PID. What's the dimension of a PID?
Oh,
1, right. So this is the 0 ideal. A bigger prime ideal actually has to be maximal. And this one is an imposter. Right? So we have a contradiction. You cannot have a chain of three distinct ideals in a PID. You have the zero ideal and every non-zero prime must be maximal, right? And in fact, another way to do this is, since this is PID, this is generated by F, and this is generated by G. G divides F, and then you can argue F divides G, and these two have to be the same. So, after all that rigmarole, this is a beautiful reduction. We reduced it to the domain case, and then made an observation about fields, polynomial rings over field. And so, the theorem is done. There can be no chain of three ideals, three prime ideals, in a community ring with one, all lying on the same prime down below. So here is the big theorem. Here's the big cheese theorem. Let's see if there's released. Let R be commutative with one. If dimension of R is n, so suppose that you have, of course, this assumes that R is finite Krull dimension, so you've got a chain of length n and nothing longer. But so if the dimension is n, then we can bound this. Adding a polynomial variable always makes the dimension bigger, and we'll see why that's true in proof. It's not too, this isn't too hard to imagine, right? Given, I think, some of the examples we've done. The beauty of this is never too big, right? So the dimension is most 2n plus 1. This is a wonderful theorem, right? Because if you start off with like a 5-dimensional domain, Krull dimension, you stack your prime 5 high, the worst case scenario is polynomial ring goes to 11, right? So, what's it?
This ring goes to.
That was a fortuitous choice, wasn't it, right? That was right. It's better than going to 10, right? It always goes to an odd because, yeah, very spinal pattern. So, it's a natural question to ask. Can you do better? And there are examples where that upper bound is actually attained. So let's see why that's true. Anybody know how to prove the lower bound? Right? How come I know that I can go at least one more? The strategy for getting one more is fairly straightforward. I can do the prime. Suppose you have a chain of length m of primes here. How can you get a chain one longer than this? Well, by the way, does anybody see how to do it? Or a way to do it? What's that? Okay. This isn't the only way to do this, of course. Okay, so now I've created one that's at least as long in Rx, right? Just by doing this, we know all these primes are, and because of these containments, we get containments, and these are all prime ideals. We need one more. You can always expand that line. And you can do all kinds of different things. You can go P0, bracket X, then P0, comma X, and P1, comma X, over P and comma. You can mix and match and do all kinds of things. So in particular, dimension of Rx is always at least n plus 1. Now, to get the other inequality here, basically we just kind of have to count. So if we have this chain, so for the upper bound, let's the upper bound, suppose that we have chain of prime star of X. Okay. So gamma 0, gamma 1, gamma. So suppose we have a length M chain of primes in Rx. So there are no consecutive things of 3 of these over the same prime below. So that is at most 2 sequential primes over the same one. And therefore, M must be less than or equal to M must be less than or equal to +1. If that's a little hard to wrap your head around, then let me show you how you inductively kind of build this. You have gamma 0. So suppose you have just P0 below that, then the most you can do is that, right? This is length 0, this is length 2 times 0 plus 1, right? If you have another prime, then the worst you can do now is to stack these two on this, right? Length 1, length 2 times 1 plus 1, and so forth and so on. The plus 1 basically comes out if we start counting 0. Right, length 2, right? Length 2 times 2 plus 1, right? And so that's what they are. Okay, any questions on that? Any questions? Okay, this is by the way, there's another failure of power series here. And so this might be a good place to kind of finish up to talk about this. We saw that for power series, so there you get a gold star for catching one of them, right? It's not true. You have this containment right here, and in general, you expect that to be strict. That was something that we used along the way that works. You get equality for polynomials, not for power series. That's did anybody pick up on another one? Here's the other one's a little more subtle. Remember, if this stays the proof, we said these three all lie over P, it doesn't matter. And one of the things that I did was I replaced so we have P is contained in gamma 0, gamma 1, and gamma 2. So PX and then y'all remember I'll replace this gamma 0 by PX because I can replace gamma 0 by this potentially smaller prime, correct? This also does not work for power series in general because if P is not finitely generated, then in fact, in general, I don't expect this to be a prime ideal. All right, so this is the smallest ideal that contains, so this is the smallest ideal in the power series ring that contains the set of elements that make up prime ideal P below. In fact, it's even worse than that, because in many cases, the radical of this is strictly contained in this, right? So remember what the radical is, right? It's the intersection of all primes. This is too big to even be the radical of this ideal, right? So this is another kind of key failing point for power series. Yeah. In fact, there can be lots and lots and lots of prime ideals between here and here in general. Okay, any questions? So next time we will start in on proof for domains, Dedekind domains. By the way, just for my own fun, how many of you have heard of Dedekind domains? Maybe you come across them in algorithm theory. How many of you have heard of proof for domains? You know, every time you use that word, you're supposed to give Bill Smith $1. I'll keep it quiet on that. Okay, any questions? All right, well, I hope you all have a good weekend and we will catch you all on Monday.